This program is brought to you by Stanford University. Please visit us at stanford.edu.
All right, so for those people who are watching on Saturday Night Live or wherever this thing is being broadcast, if you have questions that you want to communicate with me about, or you want to post some interesting insight, or I'm speaking about a physics insight, if you want to put up an interesting problem that you may have either seen or heard of or had a professor 40 years ago give you to solve and you've never been able to solve it since, or, well, that sort of thing, then rather than send it to me by email and expect me to send it out to everybody, I thought we could put these things up on a site which I created, which thus far I've got exactly one question on. Susskind's blog, Physics for Everyone, that's one word, .blogspot.com. Use it, don't abuse it. No polemics, please. I do not answer polemical questions. I've learned not to. It's taken me some time, and polemical things will be immediately eliminated. Serious physics questions, even if they're very simple, they do not have to be either deep, profound, difficult, or just some simple insights about some of the material. That'll be fine. Questions about physics, even outside the scope of the class, are fine. No questions about whether string theory is even wrong. Anyway, let's begin tonight's lecture. I put this up on the top for.
I tried to get to it. Did anybody else have that problem?
I don't know. I don't have any problem getting to it, but it may be that people are having problems getting to it. If you do have a problem, send me an email, and I'll see. I'm a complete incompetent at this. I just tried to do it. It seemed to be successful. I seem to be able to get to it. I put an announcement on it. Maybe.
More than one thread on there? I'm just trying to.
I don't know. I don't even know what a thread is.
What was the question that you got recent?
No. Came the first day. Well, recent, fairly recent, yeah. Anyway, let's keep going. If you try to use it and it doesn't work, let me know.
You have to sign in, I think. You have to define an email and go through a sign in.
Or something, yeah.
Okay.
I don't know. I'll try to find out. I'll try to get somebody who knows about these things. Okay. Let's talk about the invariance of the laws of nature under various kinds of operations. Of course, what I really have in mind is, of course, Lorentz transformations. The fact that the laws of nature do not change when we make a Lorentz transformation. But let's talk about the strategy for cooking up laws which look the same in every reference frame. The strategy is to express those laws in a form which really doesn't depend on any particular choice of coordinates. To express the laws in some physical way that does, as I said, that doesn't depend on specific coordinates, and then choose a set of coordinates and rewrite what you've expressed in a language appropriate to those coordinates. An example, the shortest distance between 2 points, the definition of a straight line is the shortest distance between 2 points, the shortest trajectory between 2 points. You can figure out what a straight line is connecting a pair of points by sticking a thumbtack. Please don't stick thumbtacks in the blackboards and the whiteboards, but you could stick a couple of thumbtacks in, take a string, pull it as tight as you can, and that will guarantee that you've found the shortest distance between those 2 points, and that you will call a straight line. In other words, the law for a straight line, this is not actually a law of physics now, this is a definition of a straight line, but it's been defined in a way that made no reference to any particular coordinates. An example of a law of physics that's closely related to this is that the path of a light ray between 2 points is a straight line. That's a law. And it now can be stated that the path of a light ray between 2 points is the shortest distance between those 2 points. That's a light ray in a vacuum. A generalization of that for light moving through various kinds of materials is that the time that it takes a light ray to go from one point to another is the shortest possible time. All right, so those, and notice again, I did not use any definition of spatial coordinates in expressing those laws. Those laws were expressed in a coordinate-independent way. But then I can then use coordinates to build myself up in mathematics and to solve some equations involving those laws. Let me give you an example. Just exactly this law here, that light travels along the shortest path, or just the problem of finding the shortest path between 2 points. All right, once I know that the shortest path, that's what I'm looking for is the shortest path, I take some coordinates, x and y. I label the 2 points of interest. I give them coordinates, x1, y1, x2, y2. I won't bother right now. And then I write down, well, first of all, I imagine a curve connecting them. I imagine a curve. In fact, I'm going to imagine all possible curves connecting them. And I break up that curve into little segments. Each little segment can be characterized by a differential, meaning a small displacement, dx and dy. So let's take a little displacement over here and label it dx and dy. Eventually, of course, we're going to go to the limit where we chop it up into smaller and smaller pieces and do some calculus. But for the moment, just call them dx and dy. And now let's write the length of the curve. The length of the curve is just the summation over all of these little differential elements of the length of each differential element. The length of each differential element we can write ds. S for length. I'm not sure why I use S for length, except it's traditional to do so. And that's equal to the square root of dx squared plus dy squared. That's, of course, the Pythagorean theorem. It does not depend on what the orientation of the axes are. With any orientation for the axes, as long, incidentally, as long as I use the same units for x and y, I would get a rather bizarre expression, as I've emphasized several times, if I used meters for x and feet for y. But as long as I use the same units, it doesn't matter which way I orient the axes on the blackboard. The expression for the length of a little differential element is still the same. And now I add them all up. I add them up by integrating. S for the total length becomes the integral, which is just the sum of all these little differential elements here, square root of dx squared plus dy squared. Now that's a strange, for some of you that may be a bit of a strange looking expression, a square root of dx squared plus dy squared. It's not really that strange. You could think of y, or you could think of x as the independent variable, and then rewrite this in another form, integral. Let's take out a factor of dx. And now in the square root, since I've taken out a factor of dx, that means I should divide what's in the square root by dx squared, and that just becomes 1 plus dy by dx squared. dy by dx squared, that's just the derivative of the dependent variable y with respect to x. And this is a perfectly good integral. if you know what y of x is. That's the length between the 2 points. And now you can set yourself the task, let me find the curve which gives the smallest value for this that connects 2 points. This, of course, is very similar to the principle of least action, which says that the trajectory of a particle in space-time sweeps out a path of least action, again, action being some kind of integral of a Lagrangian. Very similar kind of thing. But the main point here is that we've expressed the original law without coordinates, and therefore we can be sure that when we introduce coordinates, the answer will not depend on our choice of coordinates. Yes, sir?
Can you define distance without coordinates?
Sure. Tape measure. Of course, the tape measure has coordinates along it, but the point is, it doesn't matter how you reorient the axes. The tape measure will always give the same expression. So it was defined by the string or the tape measure connecting the 2 points, but without regard to how I chose the xy axes. But then, in an attempt to actually mathematically implement the mathematical problem, I introduced a set of coordinates to express the problem in a mathematical form. And so, yes, I think the problem is expressed without coordinates. It's a good question, but for the moment, I'll leave it hang as in the way that I said it. Okay, now, so that's an example. Now, what went into that example, the most important thing that went into that example mathematically was Pythagoras' theorem, that the distance between 2 points is the square root of the sum of the squares. And that does not, the sum of the squares of the coordinates, and it has exactly the same form if you were to tilt the axes. That in itself is an expression of invariance, that the distance between 2 neighboring points is invariant, meaning to say it doesn't depend on your coordinates. And of course, we're familiar with this. We've gone through it several times. Dx squared plus dy squared doesn't depend on your choice of coordinates. And the way to check that, which is exactly the sorts of things we've checked up till now, is we've taken a coordinate system, rotated the coordinate system, x, y, x prime, y prime, theta, an angle between them, and we've discovered that the law of transformation, the mathematical law of rotation of coordinates, is the law which keeps x squared plus y squared fixed, dx squared plus dy squared fixed, and the sums of squares of the components of any vector. In fact, any quantity which transforms the same way as x and y as the components of the position vector, the sums of squares will be invariant. So that's the strategy. The strategy is to find ways, to find basically all the ways of constructing quantities which are invariant under the operation that you're interested in, and then express the laws of physics, perhaps in terms of action principles. Action principles are very efficient ways of expressing laws of nature in a way that doesn't depend on coordinates. You just say, the length is minimum, or the time for a light ray to go from one place to another is minimum, or the action is minimum. All right? But you must check that the expression that you've written down for the action really doesn't depend on your choice of coordinates. And so it becomes an exercise in figuring out how to form invariants. Invariance means things which don't change when you change the coordinates in particular ways. Do you have a question?
Yeah. Question. Is this dependent on the underlying geometry?
Yes, this is dependent on the fact that the underlying geometry was Euclidean geometry, and that's a good point. There's a generalization of it, of course, the idea of geodesic in a curved space, but I'm trying now to be as simple as possible and give you the simplest examples.
When you say transformed in the same way as x and y, you mean the cosines and
Yes, exactly. Supposing I have any pair of quantities, let's call them ax and ay. Now, of course, secretly what I have in mind is the components of vectors. So let's just call them ax and ay. And I assume that they transform, which means that when you look at them from different coordinates, first of all, the components themselves depend on your choice of coordinates. And let's just assume that they transform in the form ax prime is equal to ax cosine theta, I think it's minus ay sine theta, and likewise for ay prime equals ax sine theta plus, I guess, ay cosine theta. This is the same way that x and y themselves would transform. This law of transformation from one coordinate system to another defines what we call a vector. Now, of course, we can also introduce a z-axis. And we should introduce a z-axis. I'm just too lazy to write down the more complicated transformation law, and it is more complicated when you can rotate around in 3 dimensions. But this is the idea. And once you have established that the quantities that you have are components of a vector, it follows immediately that the sums of the squares of them, ax squared plus ay squared, is invariant. What that means is that if you make such a transformation, then this will be equal to ax prime squared plus ay prime squared. All right, so establishing that a pair of components transforms as a vector allows you not only to transform them, but to write down expressions which don't change when you change your coordinates. The sums of squares of components of a vector are sort of the leading candidate for that kind of thing. Okay, so that's, and dx squared plus dy squared is a special example. Let's talk about Now, we know the analog of this for the special theory of relativity. We've gone through it a couple of times. Basically the same rules, except instead of having 2 spatial components, we have a space and a time component. Let's call it t. And then same kind of transformations, except instead of cosine and sine of theta, we have hyperbolic angles. In the same way, we would say that anything that transforms the same way as x, y, z, and t. Incidentally, did we ever talk about how y and z transform? No. Well, let's fill that gap in right now. It's exceedingly simple. Let's fill that gap. We found the transformation law x prime is equal to x times cos omega minus t, not y, t sinh omega, t prime is equal to x minus x sinh omega plus t cos omega. Now this is for a Lorentz transformation where the relative velocity between the 2 frames is along the x-axis. If we wanted to have the relative velocity along some other axis, we'd have to do something more complicated. But this is for where the 2 frames of reference are moving relative to each other right along the x-axis. What about the y and z components of vectors? Well, the y and z components of vectors simply don't change when you boost. Boost is another word for doing a Lorentz transformation along a given axis. When you do a Lorentz transformation along the x-axis, the y and z components don't change. A meter stick oriented perpendicular to its own velocity does not get Lorentz transformed. Right? The arguments for that can be found in the internet lectures on the special theory of relativity 2 or 3 quarters ago, and I'm not going to go through them now, other than to just say that the rest of the transformation law is y prime is equal to y and z prime is equal to z. Now, of course, Lorentz transformations are not the only things we can do that will keep our description of physics fixed. We can also rotate coordinates. We could rotate among x, y, and z. Those are spatial rotations. When you combine together spatial rotations with Lorentz transformations along a given axis, if you then rotate your coordinates, you can then use the rotation of coordinates to boost along a different axis. That's a complicated combination of different kinds of transformations. The question is, what are the quantities which are invariant when we have all 4 components here? Okay. Now, the combination which is invariant is more or less obvious. It's just not just t squared minus x squared. T squared minus x squared, that was proper time. That was the thing which was invariant under a boost along the x-axis, if you transform along the x-axis with a standard Lorentz transformation. But supposing I do a different transformation. Instead of doing a Lorentz transformation, I just do a rotation of coordinates. A rotation of x into y, for example. Well, if I just rotate my spatial coordinates and do nothing to time, in other words, this is just an ordinary rotation of spatial coordinates, doing absolutely nothing to time, no velocity involved, just a change of orientation, then time doesn't change. Time doesn't change if all you do is transform the orientation of your space coordinates. But x, y, and z transform into each other. So t squared minus x squared cannot possibly be invariant. In fact, when you do a rotation, the quantity which is invariant is x squared plus y squared plus z squared. That suggests that the invariant is t squared minus x squared minus y squared minus z squared. And that's correct. Under a Lorentz transformation, this Lorentz transformation here, t squared minus x squared does not change. That we've already established. All right? Furthermore, since y and z don't change, t squared minus x squared minus y squared minus z squared doesn't change. Okay? So this is the quantity which Lorentz transformations and rotations of space keep invariant. Don't change. Okay? We'll come back to that. We'll come back to that later, another time. Well, maybe today. Now, any quantity which transforms under Lorentz transformations and spatial rotations in the same way as x, y, z, and t is called a 4-vector. A 4-vector is just a quantity which transforms as the basic coordinates themselves. If you have a 4-vector, it has a time component and it has 3 space components. The difference between the square of the time component and the 3 space components squared, that always is an invariant. It's the analog of the length of a vector, but in space-time. All right, so if we have a general 4-vector, for example, just take, instead of the coordinates themselves, you have a trajectory, and you have a little interval along the trajectory. Then you have a 4-vector, which is just dt, dx, dy, and dz. And dt squared minus dx squared minus dy squared minus dz squared is the thing which is invariant for that little interval. You could add them up the same way we added up length along a curve. And that will define the proper time along the curve. So it doesn't just have to be, it's not just x and t, but x, y, z, and t, and this is the combination that forms the invariant proper distance along a curve, along a word line. It's extremely important to us to know how to form invariants, and in order to know how to form invariants, we have to specify how quantities transform. If we don't know how things transform, we don't know how to put them together to make invariants. All right, so what kind of objects are there? Well, first of all, there are 4 vectors. That's not the simplest kind of thing. There's an even simpler thing that's even simpler than a 4-vector. It's a scalar. A scalar is a thing which doesn't transform the same at all. It's the same in every reference frame. Can you think of anything which is a scalar, sometimes called an invariant? I'm not going to distinguish between invariants and scalars for this class. Can you think of anything which is an invariant? Or I heard it? Electric charge. Electric charge of a moving particle is exactly the same as a stationary particle. If you at rest watch my electron moving along, you'll ascribe to it exactly the same electric charge. I was just thinking of my name. My name is Leonardo. Okay? My name doesn't change when I start to move. It's a scalar. Some other scalars that happen in physics. Mass is a scalar. Rest mass is a scalar, yes. Mass is a scalar. But here's another scalar. dt squared minus dx squared minus dy squared minus dz squared. It's a thing which doesn't change under Lorentz transformation. Now, officially, you would call that an invariant, and but I'm just going to call it a scalar. A thing which does not change when you Lorentz transform or when you rotate. That's called an invariant. If we can build up our laws of nature out of invariants, then our laws of nature will be invariant, as simply stated. If we can build up and express the laws of nature, we can express them in terms of coordinates, as long as we express them in terms of combinations of things which are themselves invariant. All right, so we have 4 vectors. Let's just label the general 4-vector A. It has 4 components, and I'm going to label those 4 components A mu. Mu is a Greek letter. It looks like an M. It is an M. It's Greek M. And I'm going to put the index up on top. Right? For example, the simplest 4-vector would be the coordinates x mu. And what do they stand for? They stand for 4 things. They stand in particular for dt, dx, dy, and dz. I hear something's ringing. Is that in my head? That wasn't in my head. We all heard it. Okay. All right. So dx mu just stands for the quadruple of components of the 4-vector. Mu can be thought of as going over 4 distinct values, and it's usually taken to go from 0 to 3. dt is usually considered the 0th component of the vector, 1, 2, 3. That's completely arbitrary. The fact that the time component of a vector is considered its 0th component rather than its 4th component. All right. So this is the same as dx 0, ... Same thing. Now, we multiply these things together to form invariants. But we multiply them together with a funny sign. Right? The funny sign distinguishing the dt squared from the dx squared, dy squared, and dz squared. There's a notation for that. I think the notation, I'm not sure who invented the notation. Somebody probably in the 19th century. It might have been Riemann. It might have been Levi-Civita. I'm not sure who it was. But one of the early differential geometers, I don't think it was Einstein, but I'm not sure. No, I don't think so. Invented the following notation. Supposing I invent a new object, not dt, dx, dy, dz, but a new object which is exactly the same set of components, except I change the sign of the time component, dx, dy, dz. All it is the same object, except with the time component having its sign changed. Then the notation for that is dx with a subscript, like that. It's the same object, except its time component has been changed. Every time you take a vector and you change the time component by a sign, it either corresponds to raising or lowering the index. If I have the lower index object, here it is right here, and I change the sign of the time component, it becomes the upper indexed object. If I take the upper indexed object and change the sign of the time component, it becomes the lower indexed object. All right, so this is purely notation. There's no physics in it. It's purely notation for another object. But now I can rewrite that invariant, this ds squared, let's call it d tau squared, d proper time squared. Instead of writing it dt squared minus dx squared minus dy squared minus dz squared, which I get rather tired of doing, I write it in the form dx mu dx with a lower mu. Now, again, notations. This was Einstein, who realized he was writing down too many summation signs. He realized after a while that all of his summation signs in his various equations were always summations over things with upper indices and lower indices next to each other. So he got the bright idea, it was one of the brilliant extrapolations of physics, that whenever you see a thing with an upper and a lower index next to each other, automatically sum over them. Automatically. Don't even ask the question whether you sum. You do sum. dx super mu sub mu is by definition the sum over the four components. Let's see what it says. dx mu mu. Let's start with the first component, the naught component, the time component. That's just equal to dt for the upper component guy, and then for the lower component guy, it's another dt, but with a minus sign. Minus dt squared, in other words. Then there's the upper component dx and the lower component dx. They're both dx. We haven't changed any sign, so that's plus dx squared. And likewise for y and z. So this object is just shorthand for minus dt squared. Do I really want minus? Yeah, I do. No, it's fine. It's the way I want it. This is shorthand. Dx super mu, dx sub mu is shorthand for not the sums of squares, but the difference of squares, where time components always come in with an extra minus sign. Now, here's something interesting. This object is invariant. Therefore, this object is invariant. This generalizes. If we have a 4 vector which transforms the same way as dx mu, then we label dx super mu, the x, y, z, and t. If it transforms the same way as those things, then we label it with an upper index, just like dx mu is labeled here. That stands for the 4 components. I won't bother writing them, the 4 components of the vector. But we can also invent a symbol with a lower index. The only difference is the time components of these two have the opposite sign. The space components have the same sign. If we construct the analog of what's written here, namely a mu, that's the time component squared minus the space component squared, that quantity is invariant. Doesn't change under Lorentz transformation. So we're beginning to build up a calculus or a set of rules for forming invariants. And the rules are: keep track of your indices, sum over repeated indices, and make sure that an upper one always accompanies a lower one. That will build up invariants made up out of pairs of vectors. Now, it's a little more general than this. I haven't told you the story in full generality. Here's an exercise for you to prove. Supposing you have two vectors, not two-dimensional vectors, but a pair of four vectors, right? A mu and B mu. A pair of them. Both of them transform the same way as the components x, y, and z and t. Right? Then you can make an object A super mu, B sub mu. Again, that's intended, let's write down what that means. It means the time component of A times the time component, well, let's write that. It means the time component of A times the time component of B, but with a minus sign, because when you lower an index, that means a minus sign. And then plus the x component times the x component of B, plus likewise for the y component, plus AZ, BZ, B, yeah. It's the analog of the dot product between two vectors, except with a minus sign for the time components. The analog of the dot product. In fact, this piece over here is just the dot product between the spatial pieces of the vector. The time pieces come in with the opposite sign, and that you can see because one of these has a lower index, the other has an upper index. And so the relative sign of the time components is opposite. In fact, there's no difference between this and putting the lower index here and the upper index here. It doesn't matter which of the two vectors you flip the sign of the time component. The product of them will come in with a minus sign. So both of these objects here are invariants. They're like the dot product between two vectors, and the dot product between two vectors is something which doesn't change under rotation. The Lorentz invariant dot product, it's not called the dot product, the inner product, the Lorentz invariant inner product of two vectors is also something which will not change when you do Lorentz transformation. Now this is something to check. This is something you can check. Take any two 4 vectors, transform them to a new coordinate system, and then check that A mu, B mu doesn't change, that it has the same value before and after the transformation. So, as I said, we're beginning to build up a vocabulary for forming invariant quantities. Okay. Yeah.
We can transform that to polar coordinates?
Say it again?
We can transform to spherical coordinates?
No. Not spherical. No. We're doing coordinate transformations between inertial reference frames. Okay? Inertial reference frames means Cartesian coordinates and uniform velocity. Okay? We can rotate coordinates and transform along some other axis, but we're not talking about things like polar coordinates at the moment.
Inertial reference frames all refer to just the relationship between two frames?
Yeah. Well, okay, so first of all, an inertial reference frame means the spatial coordinates are Cartesian coordinates. Okay, conventional Cartesian coordinates, just x, y, and z with the usual rules for manipulating Cartesian coordinates. And it means that the two coordinate frames are in constant motion relative to each other. That's the relationship between two inertial frames. One more statement. An inertial frame, a single one, if we had one single inertial frame, then we'd be able to define an infinite number of them by transforming from one to another. All right. So you have to start with one inertial frame. One inertial frame means a frame where Newton's laws are satisfied, or where Einstein's generalization of Newton's laws are satisfied. In other words, F equals ma. Good. So that's all that goes into the idea of an inertial frame, that there's one inertial frame somewhere out there where Newton's laws are satisfied, and any other which is related by Lorentz transformation is also an inertial frame. Okay, so that's the idea of building up invariants out of 4 vectors. As I said, an even more primitive and simple concept is the invariant itself. There are invariants which are not built up out of 4 vectors. They just happen to be invariants. What's another example? The trouble is, to find examples in relativity theory, you have to know a little more physics than that. But if we were just talking about rotation of coordinates and not Lorentz transformation, there would be things which were scalars which would be very familiar. Temperature is a scalar. It doesn't matter if you hold your thermometer this way, that way, that way, this way, or that way. In other words, it doesn't matter what axes you orient your thermometer along, you get the same temperature. Pressure, air pressure, is also a scalar, an invariant. That's a little bit less obvious that if you had a pressure meter, how do you make a pressure meter? Oh, I don't know, you make a pressure meter. It's not obvious that the pressure meter, here's my pressure meter. It's not obvious that if I turn the pressure meter upside down, I get the same pressure. Why? Well, with all the air resting on it from above, you might think that it would squeeze it down more if you hold the pressure meter this way than if you hold it that way. Well, it's not true. The air is pressing as much from underneath as it is from here. Air pressure is a scalar. It doesn't matter which way you hold it. What is a pressure meter called?
Manometer.
What?
Barometer.
Manometer's not so
Isn't it a
good.
barometer?
Well, that relies on gravity.
Manometer, he said.
What's a barometer?
Barometer is a column of fluid.
Doesn't that measure air pressure? Yeah. Under gravity, yeah, that's right.
But a burden gauge does
Yeah,
that.
yeah, right.
You know,
So-
the burden gauge is a coiled piece of metal. It's got air inside it, and it winds or unwinds.
Yeah, there's many ways to make a pressure meter. You might just take a cell, put a rubber membrane over it, seal the rubber membrane, and then when you put a lot of pressure on it, the rubber membrane goes this way. If you take it off the pressure, the rubber membrane, all kinds of ways of making
But don't you need to distinguish between the actual quantity and the way you measure it? I mean, the quantity itself may be fixed, but the way you measure it may depend upon certain physical properties.
Well, sometimes the only really good definitions of quantities are through how you measure them. In fact, I think that's more or less always the case, but I get the point.
When you say it's invariant, you mean you get the same pressure when you move the frame?
No, it's invariant under rotations, not under Lorentz transformations. Right, only under rotations. So with respect to the rotations, pressure, temperature are invariants. What's a weather quantity which is not an invariant? Wind velocity. Wind velocity is what? It's a vector. It's got a magnitude and it's got a direction. And its components do depend on your orientation. The x component will change if you change what you call the x-axis. So its components are the components of a vector.
Another good scalar, humidity.
Humidity is a good, but so is wind speed. Wind speed, what does speed mean? Speed is the magnitude of the velocity. Speed is not velocity because by definition, it's the term speed officially means the magnitude of velocity. In fact, the speed is just the square root of the sums of the squares of the components of the wind velocity. So the wind speed is an invariant and therefore kind of qualifies as a scalar for me. The wind velocity, which has a sense of direction, is not a scalar. All right, so we now know what we mean by vectors, 4 vectors, scalars, and we know how to make some scalars out of 4 vectors. If we go back to the problem of, that's. Now there's another quantity, another class of quantities which are interesting, which also have 4 components. They are also 4 vectors, a little bit different. Oh, before I say that, let me just say one thing. If I have a known 4 vector, let's call it A, And I have another set of objects, b mu, which I'm not sure whether they're a 4-vector or not. I'm not sure whether they transform as a 4-vector. There's a test. You calculate in every frame of reference the inner product. And if the inner product doesn't change, if the inner product is a scalar, if the inner product of two objects, one of which is known to be a 4-vector, and the other you're testing, if that inner product doesn't change from frame to frame, in other words, supposing somebody gave you a 4-vector, they told you it was a 4-vector, and then they gave you another set of 4 quantities. They gave it to you in every frame of reference, but they didn't tell you whether it was a 4-vector or not. Then you compute the inner product a mu b mu, and if it's the same in every reference frame, then b mu is a 4-vector. That's a theorem. It's a simple elementary theorem that if you have one 4-vector and you're testing another one, if the inner product is invariant, then the result is then b must be a 4-vector. Okay, let's move on to another object. The derivative. Supposing I have a scalar quantity, such as the temperature in 3 dimensions, or some other field. Now we come to the idea of a field in space. A field in space, there are many different kinds of fields. Some fields are vector fields. For example, well, if we're just talking about 3 dimensions, wind velocity is a field. Of course, it's not a field in the sense of a fundamental field of any kind, but it is a field. It varies from place to place. It can have equations which govern it. It's a vector field. Right? Not a 4-vector field, a 3-vector field. Right? As we said, temperature, humidity are scalars. Imagine now that we have a scalar with respect to the Lorentz transformations. Let's call it phi. Phi is Greek f, and f stands for field. It's a field. It depends on position in general. X, y, z, and t. Let's just call it phi of x, where x stands for all 4 components. If it's a scalar field, it means that everybody who measures it, no matter how they're moving relative to each other, no matter what their orientation of their axes, they will agree about the value of it. Now, anybody know some examples of 4-dimensional fields which are scalars? You probably don't, because they're not familiar, but nevertheless, do you know any? Fields in space-time, fundamental fields, which happen to be.
Electrostatic field?
No, the electrostatic field is not a 4-vector. It has 3 components, first of all, so it can't be a scalar. In fact, it can't even be a 4-vector. It's only got 3 components. The magnetic field. The Higgs field. The Higgs field, right. The Higgs field is the first real fundamental scalar field that occurs in physics. Why the Higgs field is so unfamiliar to you? Well, that's an experimental physics question. Why is the Higgs field the way it is? It's an experimental physics question, theoretical physics question. But the Higgs field is a scalar field. Simply means that it doesn't depend, its value doesn't depend on how you're moving relative to it or how you're oriented relative to it.
How about a 4 velocity? 4?
Well, yes, the magnitude, good. The magnitude of any, yeah, good. Take any 4-vector field and take its magnitude. Good. That's one. Do you know any 4-vector field?
Well, the 4 velocity? You know.
No, I don't usually think of that as a field, but by field I meant a thing like a gravitational field or, you know, any, it took us a while to find a scalar. Somebody said Higgs. How about a 4-vector?
Well, the potential and the vector potential is
Yeah.
a 4-vector?
Yeah. The electromagnetic field is built out of a 4-vector, namely the components of the 4-dimensional vector potential. All right. It's a little bit tricky what its transformation properties are, but let's make it simple. The square of the, or not strictly, not the square, but the square in this sense, a mu, this could be the four-vector vector potential. This combination then of the four-vector potential with itself, the time component squared minus the space component squared, would also be a scalar.
How about energy and momentum?
No. Well, first of all, energy and momentum are not fields. They are quantities that describe a whole system. All right? But there are flows of energy, energy density, momentum density, and that sort of thing. Energy density is not a four-vector, is not a scalar. It's a three-dimensional scalar. It doesn't change when you rotate, but it does change when the system is moving relative to you. All right? You take a system with a given energy, and now you look at it from a frame of reference where you're moving very fast, it has a lot more energy. So energy and momentum form a four-vector, not a scalar.
So
Yeah.
how about things like the Hamiltonian? Is that it?
No, that's the energy. That's energy. That's energy, right? So it's a component of a four-vector. It's a four-vector together with the momentum of a system. The energy and momentum of a system form a four-vector. Well, we will have to come back to that. We'll have to come back to that because it's important. But energy and momentum come together, energy being the time component, momentum being the space component. So it's not that there aren't that many around that are familiar. What about the gravitational field? Gravitational field is not a scalar, it's not even a four-vector, it's a tensor of some kind. We're going to come to tensors. It just means it has more indices, but we'll come to that later. So it's not so easy to find examples of relativistic scalars and four vectors and so forth that you're familiar with, but the concept is easy. Just a field phi, which no matter how you're oriented relative to it, no matter how you're moving relative to it, always has the same value when measured. Okay? That's called a scalar. Now, you can differentiate scalars. You can differentiate them, you can take their partial derivatives with respect to different directions. For example, you can take the partial derivative of phi with respect to time. Let's call that phi sub t. Well, that's not quite right. Phi comma t. Phi t, just leave it phi t, like that. That stands for the derivative of phi with respect to t. We could also indicate it by a dot on top, but I want to indicate it this way. The derivative of phi with respect to time. That's one component of something that has some more components. The derivative of phi with respect to x. Let's just call that phi sub x. It's not I'm afraid I might confuse notation. This is not the t component of phi. It's the t component of a vector made out of the derivatives of phi. There are four such derivatives. Derivative of phi with respect to t, derivative of phi with respect to x, likewise z, and likewise y, I guess I missed. The four derivatives of phi can be grouped together and called partial of phi with respect to x mu. Notice we have a mu index now. Or with this simplified notation, I only introduce it to save myself from writing too many things. Just call it phi sub mu. The derivative of phi with respect to x mu. This is a complex of four objects which contain a time component and three space components. It's pretty obvious, well, at least it should be sort of psychologically obvious, psychologically meaning to say if I introduce it and I give it an index like that, it's pretty clear that it's some sort of four vector. Has four components, looks like a duck, acts like a duck, it's a four vector. It is a four vector. The only question is whether it should be thought of as a four vector with an upper component or a lower component. Incidentally, the things with upper components and lower components transform slightly differently. There are some funny minus signs when you transform the vectors with the lower index. In fact, if you take the Lorentz transformation and every time you see a time component, change the sign of it, you get the transformation properties of the object with the lower index. So lower index objects transform slightly different than upper index objects. They are different, and they differ only in the sign of the time component. Should we identify d phi by dx mu as a thing with an upper index or a lower index? Okay. That's an interesting question. The answer is with a lower index, consistent with what I've written here. But how do we prove that? How do we prove that that d phi by dx mu is a 4-vector of the lower kind? Incidentally, what's the name for things with upper indices and lower indices? Anybody remember? Covariant and contravariant. The ones with the upper indices are called contravariant? Covariant. And the ones with lower indices are called contravariant. Co is low.
Covariant and low. Co is low.
Well, then everybody had it backwards. I never remember. I can't remember. I just call them the upper guys and the lower guys. And
The derivatives have the same kind of coordinates as...
I would have called them covariant. Yeah, I would call this covariant, but I may have it backward. And dx mu, I would call contravariant, but I may have it backward. I think I'm right. Yeah. Okay, let's try to prove that d phi by dx mu is a covariant, or the covariant components of a 4-vector. Now, here's what we need to do. If we can find some known 4-vector, and we combine it together with the thing which we're testing, and what we get out is a scalar, then we're assured that the thing that we're testing is a 4-vector. In particular, if we take a known thing which corresponds to a contravariant 4-vector, and we combine it together with something which we suspect is a covariant 4-vector, and we always get a scalar, we always get the same thing out, then we're assured that the thing with the lower index here really does transform in the right way. All right, we have something. Yeah.
Naive kind of question about your notation there.
Say it again?
Naive kind of question.
Naive question, go ahead.
Yeah, the x has a mu upper,
Yeah.
but the phi has a mu lower.
This just means derivative with respect to x mu.
He's troubled because x is x mu.
Yeah,
Oh, you're troubled because this one is upstairs and this one's downstairs. Yeah, I know, but the dx, the derivative with respect to dx is down below the fraction bar. Doesn't that convince you? It shouldn't. The only thing that should convince you is a proper test. So let's do the proper test.
I think the image that I've heard is supposed to work is the tangent covaries with the surface.
Let him do it, Mike.
And that's why you have the derivatives as components.
I don't get it, but let's do the test. The test is to find some known covariant 4-vector with an upper index. Multiply it together with this thing, sum over mu, and check whether the result is the same in every reference frame. Right? Anybody got a suggestion for a known? Yeah, here's the test. Take 2 points, 2 neighboring points. Phi is, of course, a field. It varies from point to point. Right? It varies from point to point, but it's important to realize that the sum of scalars is another scalar, the difference of scalars is a scalar. All right, so let's take these 2 points, which are separated by a small distance dx mu. Dx mu are the components of the coordinates, the coordinate components of the displacement between the 2 points. Now this is a known 4-vector. It's a known contravariant 4-vector that transforms as a covariant, as a 4-vector. Let's multiply it by d phi by dx mu. Dx. And sum over mu. Anybody know what this quantity is? It's partial derivative of phi with respect to t times dt plus partial of derivative of phi with respect to x dx plus partial of derivative of phi with respect to y dy. It's just the difference of phi at the 2 endpoints. Let's call this endpoint 2. Let's call this endpoint 1. You could call it just d phi. It's the difference of phi at 2 minus phi at 1. It's the change in phi when you move in one direction times the change in x, etc., etc. It just gives you the small change in phi when you move from one point to another. Phi is a scalar. Differences of scalars are scalars. So the right-hand side is a scalar. The left-hand side is the product of a known contravariant vector with something that we're testing. We've successfully tested that d phi by dx mu is a 4-vector of the covariant kind, of the kind with the lower index.
And that's because it does not change. Dx is equal to 0.
Right. So now we found some more interesting objects. Derivatives of fields. We have contravariant vectors dx mu. We have covariant vectors d phi by dx mu. We can turn a contravariant vector into a covariant vector by changing the sign of its time component. So we can invent the covariant version of a particular contravariant vector. In like manner, this of course is phi sub mu. In like manner, we can invent a contravariant version of this derivative here. How? Just by changing the sign of the time component, in which case it becomes phi super mu with a superscript. The only difference is both of these phi's are made up out of derivatives of phi with respect to time and space, but the time component of this is minus the derivative of phi with respect to time. So this complex here stands for d phi by dt, d phi by dx, and the others. This one stands for minus d phi by dt and d phi by dx. What happens if we multiply this one by this one? In other words, what happens if we take phi with a super mu and multiply it by phi with a sub mu and sum over mu? What does that give? Well, it gives us derivative of phi with respect to t squared with a minus sign, and then plus signs the square of d phi by dx and the square of d phi by dy and the square of d phi by dz. Is that an invariant? Yes, it's an invariant because it's composed out of an upper index and a lower index, and that's our rule. So, for example, we've now discovered a new scalar. The new scalar is minus d phi by dt squared plus d phi by dx squared plus d phi by dy squared plus d phi by dz squared. Any observer in any inertial reference frame, any Lorentz frame, who measures in his own reference frame the components of the derivatives of phi with respect to time, with respect to space, and those derivatives will not agree in different frames of reference. They're components of a vector. But if we take the combination minus d phi by dt squared plus d phi by dx squared, d phi dy squared, d phi dz squared, that quantity is the same in every reference frame and is a scalar. So we have a scalar. And in shorthand notation, it's just d mu phi d super mu phi. So again, I emphasize what we're generating is a kind of calculus of invariants, ways of building invariants out of vectors, derivatives, differentials, for vectors of various kinds. All right, let's take a little break, and then we'll come back to the waves moving on a string, but in light of what we've learned up till now. All right, so let me write down on the blackboard the scalar that we've discovered. Take a scalar and begin with a scalar and construct the components of its derivatives. In other words, we could call it its gradient, for vector, d phi by dx mu. So many ways to write it. All right, we could write it this way. We could write it this way. They all mean the same thing. And we could write it just phi mu. All mean the same thing. Okay. We can also construct a contravariant version of this. As was pointed out by somebody here, strictly speaking, when you construct a contravariant vector, you're talking about a thing in a different space, the dual space, but let's not worry about that. That's a fine point of mathematics, which is important and interesting, but we don't need to be so technical at this point. You just change the sign of the time component, and I'm not going to try to write this one, or we can write d super mu phi.
So we could just lower the mu, right?
Yeah, I could put it down here, couldn't I? A lower thing in the denominator means an upper thing. d super mu phi or phi super mu. All mean the same thing. These two sets of objects are the same objects with the time component having the opposite sign. And then we discovered that the combination d mu phi is also a scalar. And in fact, what is it? It's dt phi squared minus dx phi squared minus dy phi squared. All right, I'll write it. I never really understood why neat notations were invented until I started teaching. You get really sick of writing things like this. Here it is. D sub mu, d super mu. Oh, thank you. Minus signs the other way. Incidentally, they're scalars no matter which way you're, with either way they're a scalar, but with the minus sign here it corresponds to the definitions that I've already used.
You could just use i's for the other one.
I.
For the spacing.
I?
You use I for the space index and mu for the forward.
Oh, you could, yeah. Right. Or naught for the fourth index and I for that, yeah. Now do keep in mind I've left out some speeds of light. I've set the speed of light equal to 1. there are some places you can restore the speeds of light just by dimensional analysis. I won't do it here and now. Okay, let's come back to the problem that we addressed last time of a string vibrating in the plane perpendicular to the orientation of the length of the violin. We define the vertical coordinate of the string by calling it phi. The string is vibrating. The vertical coordinate of any point, remember the string was made up of a bunch of points. We took a limit in which the points became denser and denser, and basically phi sub I, which was the height. I does not stand for a direction of space. It stands for the ith particle along the chain, phi being the vertical direction, x being the horizontal direction, phi being the vertical direction. Phi morphed into a field which just became phi of x. Phi of x was the displacement in the vertical direction of the field. Incidentally, we will either, I had hoped to do it today. I don't think I'll get to it. I was going to study strings which vibrate both vertically and horizontally. There's an interesting point there, but we could also do strings which vibrate along their own direction, but I'm not going to do that tonight. All right, so there's phi sub I, meaning the phi coordinate of the ith particle, became phi of x. We also wrote down an action principle. Let me just remind you quickly what that action principle was. It contained, in the discrete form, before we took the limit, it contained kinetic terms and potential terms. The kinetic terms, now I'm going to use sum because I'm not summing over indices, I'm summing over particles. Sum over all the particles, phi I dot squared over 2, and then there was a mass for each particle, which I took to be epsilon, or proportional to epsilon. Epsilon was the x separation between neighboring points on the string, or neighboring sites. And then there was another term. This was the Lagrangian I'm writing down. This was the kinetic energy, and then minus the potential energy, and the potential energy had a spring constant, which was 1 over epsilon. I think I put a c squared there. Later on, we're going to set c to 1 again. And then I think it was phi I minus phi I plus 1 squared. Okay, everybody remember that? Anybody? Oh, it is a 2. All right, spring constant went like 1 over epsilon, mass went like epsilon. And we played with it. We worked out the equations of motion, took the continuum limit. The continuum limit is the limit in which epsilon shrinks to 0, and in which we replace the discrete variable phi I by phi of x. And let me remind you in particular what happened to the Lagrangian. Oh, there was the Lagrangian and there was the action. Here's the Lagrangian. And the action is the integral dt from some initial starting point to some end point of the Lagrangian itself. Well, when we took the limit in which we let the epsilon shrink to 0, something nice happened. Let's recall what it was. We did it 2 ways. One way we did it was to write the equation of motion itself, and then take the limit in the equation of motion. What we got was the wave equation. Let me write down the wave equation. It was d second phi by dt squared. That, of course, is just the acceleration of a point on the string, the vertical acceleration of a point on the string, the second derivative with respect to time. And that was equal, is it, c squared, let's just write it, minus c squared, second derivative of phi with respect to x squared. That was not exactly what we had. What we had was, let me remind you, what we had was, well, we had some discrete form of the second derivative. I'm not going to repeat it. Go back to your notes. We worked out the equation of motion and then took the limit that epsilon went to 0, replacing differences by derivatives. There was a difference of a difference, which became a second derivative. Everybody remember that? Good. Okay. Now, we could have done the same operation by figuring out what happens to the Lagrangian in the same limit, and we did so. We actually did so. We found out that this term here, the first term, first of all, the sum became an integral, dx. The phi dot squared, well, that's just the derivative of phi with respect to t squared. The fact that 1/2 is still there. And then minus, I'm going to set c equal to 1. Now, c in the original problem had nothing to do with the speed of light. It had to do with the speed of propagation up and down a violin string. Of course, secretly, we all knew that eventually I was going to say it was the speed of light, not because violin strings move with the speed of light, but because this was just a model for a relativistic field. All right, so let's set c equal to 1, and this term became minus d phi by dx squared. Integral dx. That is the Lagrangian, but it's not the action. The action is you take the Lagrangian and integrate it over time. The Lagrangian itself is an integral over space. What it's doing is it's adding up all the points along the string. That's what this x integration is doing here. Adding up all the points. Let me move the dx to the back here. All right, so dx integration adds up all the points along the string. It's a stand-in for the sum over I, but the integral dt, that converts the Lagrangian into an action, the thing which goes into the principle of least action. All we have to do is write dt here. Did I hear a question? No question.
He wants another integral sign, I guess.
No. One integral sign is enough. The number of integrations is told to you by how many d's you have. Okay, you really want me to write another integral? No. All right. So it's an integral over space and time. In the problem that we set up, space extended over some finite interval from the peg to the bridge. So space was some finite interval. And in the principle of least action, we also introduce an interval in time. The time from the start to the end of the process. We introduce initial conditions at the beginning, final conditions at the end, and we ask what is the history of the system which interpolates between the initial state and the final state, and which minimizes the action. So there's also an initial time and a final time. And the action becomes an integral of a certain quantity which involves the field and its derivatives, integrated over this region. This is not supposed to represent the string. It's just supposed to color in the region where you do the integral. Well, by now, of course, you've made the connection that at least for this one-dimensional problem, what goes here is exactly the scalar. Of course, that's only true if we take the c to be the speed of light. But this has exactly the same form as the scalar. I've eliminated two dimensions. Y and z don't play any role in all of this. We're only talking about motion of waves up and down a particular axis now, the x-axis. And it's no accident. It's not an accident that the Lagrangian here takes this form of a quantity which appears to be Lorentz invariant, which appears to be a scalar. What this tells us, well, what do you think it tells us about the equations which follow from this Lagrangian? Here's the principle. The principle is minimize the action, with the action being defined by this integral over space and time of a certain scalar.
The equations of motion will be Lorentz invariant?
The equations of motion are Lorentz invariant.
So if you start with the scalar, Lagrangian,
Right.
you wind up with a Lorentz invariant
That's right.
equations of motion.
That's right. If you start with a scalar for the Lagrangian, then this, okay, let's get some terminology right now. Script L, by the time we went this far, well, no, script L is the Lagrangian. Let's call it capital L. But capital L itself is an integral over space. The Lagrangian is an integral over space. Let's get all the things down. Yeah, let me write them down in one place over here. The Lagrangian began as a sum over I. It morphed into an integral dx. The thing that went into the integral, the integrand, I can call script L. What is it composed out of? It's composed out of the derivatives. It's a function of the derivatives of phi with respect to the various coordinates. It could also involve phi. I mean, this is not the most general thing we can write down. This is what we got by hooking springs together with violin strings. This is called the Lagrange density. It's called the Lagrange density because you integrate it over space to find the full Lagrangian. But then you go to the action. The action is the integral of L over time. And that becomes the integral over x and t of the same quantity, of the same Lagrange density. I won't bother writing down what it depends on. So you can almost think that the Lagrange density is a kind of action density. In fact, that's what it is. It's the action per unit space-time volume, per dx dt. That's what this Lagrange density is. You can think of it as a thing that you integrate over space to find the Lagrangian, and so it's the Lagrange density, but it's also the thing that you integrate over space and time to find the action. So it can properly be called the action density, but the action density in space-time, not the action density in space, but the action density in space-time. All right, now,
Does that mean it's a scalar?
the Lagrange density is a scalar. Well, let's put it this way. If the Lagrange density is a scalar, then the equations are invariant under Lorentz transformation. All right? That's the criteria for an action which will give Lorentz invariant equations, that the action itself be invariant, and that entails the integrand being a scalar. So if the integrand is a scalar, the equations of a theory will be Lorentz invariant. I've left out some details, and even some logically important details, but I think we've captured the essence of the idea of invariance and how you build invariant laws of nature from invariant action principles. Okay? Let's go a little bit farther. Supposing we actually wanted to construct a field that vibrated around, not along an axis, along a violin string, but that moved throughout all of space and time, x, y, z, and t. The strategy is quite clear. All we have to do in order to find the Lorentz invariant description in 4-dimensional space, this is in 2-dimensional space, one time and one space. All we have to do is fill out the rest of this expression and write the action equals 1/2 the integral, now this becomes a 4-dimensional integral, not a 2-dimensional integral. A 4-dimensional integral, I could write the x dy dz dt, but I can also just write d4x. That's the standard symbol for integrating the x dy dz dt, d4x, and it means an integral over volume elements in space-time. Not in space, but in space-time. And then d mu phi. Now, I have something wrong here. What I have wrong here is that the kinetic energy comes in with a plus sign. Here, I've written it in such a way that it has a minus sign, so normally you would put a minus there. All right, with the minus there, it's just equal to integral, let's call it phi t squared minus phi x squared minus phi y squared minus phi z squared, where you know what I mean by phi sub t and phi sub x, y, and z, just the derivatives. All right. This is a scalar. The action itself is invariant, the same in every reference frame, and therefore the problem that you set up when you say, let me find what minimizes the action, doesn't really depend on the frame of reference. Now let's talk about, let's see, how much more time do we have? We have a little more time. You know, I think I'm going to stop here. I think we've done enough for tonight and take some questions. What I wanted to talk about was, given a Lagrange density, given a script L, how do you generate the equations of motion in a simple way? The overall strategy is clear, minimize the action. But how do you convert that to differential equations? How do you convert that to wave equations? And we'll talk about that next time, but I'll just remind you very quickly that the same question occurs when thinking about particle mechanics. We had an action which depended on the trajectory of a particle. We wanted to minimize that action. That sounds like a global problem that involves the whole trajectory, but we converted it to a differential equation which only involved the first and second derivatives of the motion. And we did it by focusing on a little piece over here and saying, if we've actually minimized the action, then we must have also minimized the action between these 2 points if everything else is kept fixed. And so we just take these 2 points and we explore around what trajectory between these 2 points minimizes the action between the neighboring points, and that's what gave us a local differential equation. We could either concentrate on the global issue or we could concentrate on it locally, minimize the action between 2 nearby points, and that gives the local differential equations. We're going to do exactly the same thing next time. I'll probably just write down the answer, but let me tell you what the strategy is. We have some space-time region, and we want to minimize the action. We want to know what field configuration, in other words, what history of the field. What does a history mean? In the case of the violin string, it means a history of all the points on the string, an entire motion of the string from beginning to end. In the case of a general field, it means the entire motion of that field in space and time. What motion of the field in space and time minimizes the action? We could try to solve that by exploring all possible functions that can fit in this space-time box, but we could also do it another way. We could say, supposing we know the value of the field on some little boundary here. All right? What if we know the value of the field? If somebody told us that the solution of the problem involves the field having a certain value on a little region, on the boundary of a little region, and asked us to figure out what it was doing inside, we would say, all we have to do is minimize the action in that little region there, subject to the constraint that it has some fixed value on the boundary. That gives us differential equations. In the same way that focusing on a little piece of the trajectory took us from the action principle basically to F equals ma, doing the same thing, taking a little region and requiring that the action be minimal within that little region, takes us from this grand action principle to the local differential wave equations. Where are we? I think we erased the wave equation. In fact, I don't even think we ever wrote it down. Well, I'll write it down next time.
Well,
So-
actually, you abbreviated it pretty much like that.
Well, here's the action.
Well,
Let me remind you what the wave equation was. I think I did write it down. Yeah, it was second derivative of phi with respect to t squared minus second derivative of phi with respect to x squared is equal to 0. So we either could think of that as the equation coming from this discrete problem of a bunch of points connected by springs, or we can think about it in a more space-timey kind of way and say it's the equation that comes by minimizing the action over some tiny little patch of space-time, given that we had already figured out what was going on the boundary of that region. And that defines for us the wave equation. So it's back and forth between grand global principles which have the advantage that they tell us manifestly that the theory doesn't depend on the particular Lorentz frame on the one hand, and going back and forth to differential equations, which are, of course, in general, easier to, they're the things you want to write down and solve using differential equation theory. Okay, I think we're about finished for tonight, and next time we'll get into the business of actually writing down field equations and solving them from various action principles like this. Yeah?
Isn't the wave equation that you wrote down just Lagrangian density set equal to?
No. These are second derivatives. These are squares of first derivatives. Right, that was a perfect question to ask because I meant to say it and I forgot. Incidentally, can you think of something else we might add into this Lagrangian here that would still keep it invariant?
yeah, any constant,
Well, any constant, of course.
any velocity? Or
We want what's in here to be a scalar. Phi is a scalar. We could add phi in. We could add phi squared, phi cubed, phi fourth, function of phi. Any function of phi we could add in there. And we will do so. Okay?
Oh, yeah.
Yeah.
Underneath the board, the last expression you wrote there, the integral, should be also d4x.
Here.
After that, yeah.
Yeah.
Good.
Good. Okay, d4x, of course, is just another convenient notation that saves me writing dt, dx, dy, dz.
Yeah. That has its own transformation property, I guess, the d4x.
Good. That is a good point. The question is, how does the differential quantity itself transform? And the answer is it's a scalar. Right.
I can't quite hear you.
The answer is that d4x is itself a scalar. All right. We'll come back to that. That's an important point. When I said before I left out a little piece of logic, it had to do with that. It's the volume element. It's not completely obvious that that is a invariant, but it is. Yeah.
The model starts out with the spring constants, with two constants, the spring constants and the mass for a unit string. And it ends up with just one constant, c.
Yeah.
Do you ever get to break c into two parts, a mass and a spring?
Yeah. Okay. So let's all right. So let's put back the constants. I always want there to be an epsilon here and an epsilon here, because if those epsilons aren't there, then it doesn't scale correctly when you take the limit. But we could put in another constant mu here, and we have a constant there already, so I don't need another constant. So in principle, there could be two constants there, right? Who asked me the question?
Yeah, I asked it. I
Yeah.
just want to know, are they separately measurable, or do you only get...
Yeah, they're separately measurable if we know exactly what phi means. If we really knew that phi meant height of this thing in meters, then we could measure it, yes. But we can always take phi and mu and absorb it into phi. We could invent a new variable instead of phi. Let's call it, I don't know, what's another Greek letter?
Alpha.
No, I don't like alpha. Nobody ever uses alpha for fields. Chi. Chi, good, chi. Chi. And let chi equal the square root of mu times phi. All right? All I've done is taken the square root of mu and grouped it with phi here. Then, did I write what I wanted to write? Yeah. Then chi squared, first of all, is mu times phi squared. And the same is true of derivatives. Chi dot squared is mu times phi dot squared, right? It's also true that I would have to manipulate this over here, but by the time I'm finished, I could eliminate the constant out of here by redefining the field with a square root of mu there. All right? So I can redefine phi, and it'll be at the cost of changing the constant over here. Okay? When I write, let's write it this way. When I write that phi is equal to chi over the square root of mu, and I do it everywhere. So I do it here, I do it here. It'll eliminate the mu out of here, but it'll show up again over here. Okay? It'll show up in the denominator over here, but then I can just combine it with c and say it was just a change of the c that was here. So really, there's only one constant that really enters into the propagation of waves. And what it comes down to is the speed of propagation. That's all that's really left over in the end after you make use of all the freedom that you have in changing units. It's basically a change of unit of the phi axis. So that's the answer to that question. There's only one.
Think of it as a mass instead of a propagation speed?
Well, it's the propagation speed along a string is composed out of two things. It's composed out of the mass density and the tension in the string. All right? And those, and basically these are these two constants, but they can be combined together into a single variable.
Think of them as being the other way around.
What's that?
Can you think of them as being the other way around? You can roll your speed of propagation kind of into the mass of the system.
Yeah, but you can always rewrite, by changing the units of phi, you can always rewrite it so that there's only one constant and it's over here. You could also rewrite it so the constant over here was 1 and the constant shows up over here. But you have one constant that physically corresponds to the speed of propagation, and that's all. For this wave equation, for this here. If you have another term, for example, phi squared, there could be a numerical coefficient in front of that, and that would be new stuff. That would be a new constant. And, yeah.
Many semesters ago, in terms, when you started describing string theory, you started with the same model of little springs, and
yeah, there's only so many different things in physics that you can solve, and so.
I was going to say, is there any significance that you started with the same model, or is it just?
Yeah, it's the only thing I know.
You're very lucky.
Yeah. Well, is there a significance? Not direct. Not direct. Right. Okay, good. If there are no other questions, let's, and we're going to go home and we're all going to make up physics questions and put them on the blog.
The preceding program is copyrighted by Stanford University. Please visit us at stanford.edu.